The other team members from the lab portion of the class are Sean McLean and Shane Stainfield. We did the flow system, or the filter wash system. So we're going to cover the operating curve and the step response for our system, and the ranges for the step response, and then the data for each of those tests, and also the results from those. So this is our system. Here we have a flow recording controller at the top, the FRC, which is attached to a flow control actuator, and then the pump, and then there's also the flow transmitter. So what happens is the user puts an input into the flow recording controller, which is implemented by the flow control actuator, which controls the pump, and the pump causes the flow through the system, which is recorded by the flow transmitter, and then sent to the, it's measured by the flow transmitter, then sent to the FRC, flow recording controller. So in summary of the system, you put an input into the system, a power input into the system to the pump, and then the pump pumps water through the system, and we can measure the output in pounds per minute. Here's an example of the steady state tests. We did each of these and we averaged them. Averaged the steady state operating output to make our SSOC curve. So here we have an average of 18 pounds per second after it reaches steady state. And the range for here is, this is 90% input. This is our steady state operating curve. As you can see, between about 35 and 65% input, the system does not act very predictably. So the steady state operating range would be between 65 and 100%. And there we have a k-value of 0.3, or the slope of that would be 0.3. I'm not sure if that's actually gain. After that, we worked on step function analysis. So to do that, we would examine the step response and the steady state operating range. So that would be between 65 and 100%. I think we actually went down to 55 to begin this, and we did it in 15% step increments. So each test, so we did 3 different ranges. We did 55 to 70, and then 70 to 85, and then 85 to 100. And we did 3 step ups and 3 step downs for tests for each operating range. So here's an example for 55 to 70%. So you can see where the input is the blue line and the brown line is the output, or the brown blob, I should say. Here's some more. Shows the size of the step. So we get about 6 pounds per minute increase from 15% increase power in this case. So after that, we evaluated it, and we got gain, and the time constant, and the dead time. So here are results for gain for each of the tests. And it should be noted at 55 to 70%, the step down uncertainty is very small. It was very consistent results in that range. But in the other ranges, it's more. There's a little bit larger margin of uncertainty. And the same with the step up in that range. This is for dead time, though. Excuse me. So that's for dead time. And here's our time constants. In the 85 to 100% range, there's greater uncertainty than the rest. Here's some results from our modeling. This is from 85 to 100%. This is just one example. So here we have a K of 0.38, which is very comparable to the previous that we got from the graphical checks. And the same with the dead time and the time constant. And it's pretty close from the template we used. It matches the curve pretty well. Here's a step down. And again, we got very close results, very similar results to each. So in conclusion, the best operating range for this system is between 65 and 100%. And then tau and T0, or the time, or dead time, and the gain were found for 15% increases in steps from 55 to 100%. Those were broken up in 3 equal sections, 15%. And then we also concluded that the results from the modeling techniques were found to be very similar to the graphical results. Anybody have questions?